In this video, we will be reviewing exponential functions and logarithms. The five main concepts that we are going to be talking about within this video are first compound interest, rewriting exponential equations, logarithmic properties, solving exponential logarithm equations, and then the applications of when we use exponential and logarithm equations. The five main concepts are color-coded, so that way throughout this video, if you would like to fast forward through one of the topics, you may do so by finding the next colored set of slides. Throughout this video, I encourage you to take good notes, as this will be your foundation for reviewing of this chapter and of these concepts for the final. When reviewing compound interest, the two things you're going to want to know are the formulas. The first one is if you are compounding continuously, you will be using A equals PE to the RT power, where A is your outcome, P is your principal, it's your initial value, E is that arbitrary value, and then R is your rate, and T is your time. Compound interest that varies if it's semi-annually, quarterly, monthly, weekly, daily, etc. Changes how often that rate gets applied to that principal income. So that is why we have a different formula in which we use this one right here, where P again represents your principal, your starting amount, R is your rate, N is the amount of times that rate gets applied. So if it's monthly, it's going to be 12. If it's quarterly, that's going to be 4 times. If it's weekly, it's 52 times per year is what you're looking at. Okay, so daily would be 365 and so forth. Here's our first example regarding compound interest. One thing that, as you read this problem, I want you to recognize that 9,000 is your initial investment. So that's going to be our P value. The 6% is our annual interest rate, and that is being compounded semi-annually, so twice a year. And we're looking at it for 4 years. So we're wanting to know how much money is going to be in our account. So that means that we're going to be using the formula A equals P times 1 plus R over N times N to the T power. And now we just have to plug in the appropriate values in their correct location. So I'm going to have A equal 9,000 times 1 plus, we need to turn that percentage into a decimal point, so that's going to be 0.06, divided by how many times that interest rate is going to be applied throughout the year, and we said that's semi-annually, so that's going to be 2 times per year. And then for our exponent, we're going to have 2 times 4, because we're looking at 4 years. Now I can just go ahead and type that into my calculator, making sure that I use parentheses accordingly. You may also want to add an extra parentheses surrounding that division right there with inside that first round of parentheses. If you typed it into your calculator correctly, you should get the amount that you would have in your account after those 4 years to be $11,400 and approximately 93 cents. In this example, it's another compound interest example, but this time it's not giving you the initial investment, that P value. You are going to be ending up having to solve for that. They do give you your rate. They do tell you that you're compounding monthly. They do tell you your ending value and for how long. So all we need to do is use that same formula we used in the previous example and plug in our values appropriately to be able to solve. So you can see here that I used the same formula as last time. I plugged the 12,000 in for my outcome value of how much was going to be in the account at the end. I don't know my initial or my principal value, which is the P. And then 9%, I turn that into a decimal. And then because I'm compounding monthly, that is why N is 12. And then multiplying it by the 6 for the 6 years. So now what I'm going to do is I'm going to simplify this piece right here. Just typing that into my calculator so that way in the end I can divide by that to get P by itself. So when I simplified that, I got 1.7125 approximately, and that's being multiplied by P. So I divided that from both sides to get a final P value of $7,007.08. Here's an example of compound interest that we'll be using the other equation for, or other formula for. Here's my initial investment that I just highlighted, and I'm compounding continuously at a rate of 7.2% for 3 years. So because of the fact that we're being compounded continuously, that is why we're going to be using that other formula where A equals P times E to the RT. Now that RT is an exponent, so now we're just going to simply plug in the values. Again, your decimal or your percentage needs to be written as a decimal to find out how much money we'll have in that account. So I went ahead and I plugged in my principal, and then I converted my percentage into a decimal and multiplied it by the number of years. Now when you type this into your calculator, you're going to want to type in first your principal, and then you're going to hit second natural log, which is going to be on the left side of your graphing calculator. This will provide you with e to the some power, and you can just go ahead and type in 0.072 times 3. If you do so correctly, you will end up with the $10,242.82 to be had in that account for this investment. This concludes the section on compound interest. The next section that we'll be looking at will be rewriting exponential equations. In this section, we will be looking at primarily the horizontal shift can be written as a vertical shift and how that works out. So we're going to take our beginning expression here, 2 to the 3x minus 5 power. And what ends up happening is you split the base and the exponent up into two separate, and then, or sometimes even more to continue simplifying as such. So 2 to the third is 8, because that's 2 times 2 times 2. And then 2 to the negative fifth. What you need to do is remember your exponent properties, where 2 to the fifth power is 32, but because of that negative, it's being written as a fraction. So after simplifying all of this, it leads us into this next set of multiplication here. So to move from here to the 1/4 times 2 to the x, you can see where we get the 2 to the x from, and that's from this part right here. But how do we get this 8 and 132 to become 1/4? And that's with multiplication. When you multiply fractions, you multiply straight across. Well, both 8 and 32 are divisible by 4. So, divisible by 8. So 8 divided by 8 is 1, and 32 divided by 8 is 4. And so that's why we're left with that 1/4, which is your vertical, I shouldn't say shift, stretch. That's what I meant to say. Make sure you're always reducing your fractions when moving forward. So we'll have two examples on this idea. Make sure you're taking good notes and moving forward. So the first thing to do when rewriting an exponential equation, when rewriting a vertical stretch from a horizontal shift, remember that you want to split up your exponent to be separated whichever that symbol is. From there, you can even separate it even further. So 3 squared times 3 to the x power times 3 to the 4th. And so this will lead us into 3 squared being 9 times 3 to the x times 3 to the 4th, which is 81. Then what I can go ahead and do is multiply that 9 times 81 to get my vertical stretch to be 729 times 3 to the x. And that would be my final answer. So only time that you'll have a fraction is when that plus sign is actually read with a minus or a negative. Let's take a look at another example. Again, we're doing the same thing. This time we're separating with a base of 5 to the 4x, and then multiplying that by 5 to the negative 3 power. Again, we can simplify that even further. 5 to the 4th times 5 to the x times 5 to the negative 3rd power. Then I would just go ahead and simplify what 5 to the 4th is, which is 625, times 5 to the x times 5 to the negative 3rd. So 5 to the 3rd is 125, but because of that negative, that makes it into a fraction, and it can be written as such. So the next thing that we're going to do is we're going to combine these two values together to simplify our expression even further. So when combining those two together, you can see that I did a little bit of work off here to the side. I took that 6 times 1/25 and equaling that to 5. So then you can see that I have the 5 to the x power, but then my vertical stretch coming from this value over here off to the right after simplifying that. The next part of this video is going to be talking about the logarithm properties. And there are several logarithm properties, so go ahead and pause the video at this time to make sure you copy all of these down. And don't forget the change of base formula over there off to the right side as well. These will be good for you to use when condensing logarithms, especially when you are going to begin solving a logarithm equation. So we'll be, so again, pause this video and then we'll go ahead and do some examples together on how to condense a logarithm expression. So when condensing a logarithm expression, the first thing you do want to check is to make sure that the bases of your logarithm are the same. Otherwise, you're unable to use any of the logarithm properties. The next thing that I'm going to suggest that you do is you take your values that are in front of your logarithm and you bring them back using that exponent or the power rule property, allowing those multiples to then be written as an exponent. So what that looks like is log base 6 of a to the 3rd power minus log base 6 of b to the 6th power. The next thing then that you're going to need to do to simplify is take care of that minus sign. And that's the quotient rule. When you're condensing using minus, it's the same thing as division. So whichever value comes first becomes the numerator, and the second value becomes the denominator. My final answer for condensing would be log base 6 of a to the 3rd power divided by b to the 6th power. And that's the furthest I can go regarding simplifying that expression. Let's go ahead and take a look at another example. So here's another example that looks a little bit more complicated than the first. But really what you can do is, instead of it being written as dividing by 3, you can change all of that so it's written as a 1/3 being multiplied by each one of those logarithms. So I can just pull that 1/3 out in the front. Then thinking back all the way to your algebra skills, Because these are all being multiplied by 1/3, I can pull that multiple out and have it be written as 1/3 times the log of 7 to the x plus log 7 base 7 of y plus log base 7 of z. Then, using my power rule, so all I did was factor there. So now I'm going to take my power rule, I'm going to bring that back up as an exponent, and the plus signs, if you look back to your notes, mean multiplication, and they all have the same bases. So that's why I can do all of this. So what happens is you'll have the log base 7 of x times y times z. So all I did was, because that plus sign turns into multiplication, I just combined all of those together. And then also, this is being raised to that 1/3 power. Now remember, when you have a fraction as an exponent, it's the same thing as being a radical. So if I write you a little side note, if I have x to the a power, and then you have that b radical, that's the same thing as saying x to the a divided by b power. So I'm going to change my fraction exponent so it's actually written as a radical. And what that's going to look like is log base 7, and then it's going to become a cube root of x, y, z. So that was a little bit more complicated. It had a little bit more algebra skills involved with the use of factoring and then remembering that exponent to radical conversion. So here's another example in which we're going to condense. Definitely more complicated just because of all the different properties that are happening within this logarithmic expression, but nothing that can't be condensed down to a single logarithm. So one of the things that we can do is definitely take this 1/2 and go ahead and make it an exponent. And then another thing that we can do is go ahead and take care of that addition sign in the back and turn that into multiplication. What that ends up looking like is the following expression. So after taking care of that addition sign and making that into multiplication, and then also taking that 1/2 and making that into an exponent, you can go ahead and simplify this multiplication to have it say 6y squared within that log base 7. And then also, there's a lot more simplifying that we can do within that first logarithm expression as well. And what we can do is remember what it means to be to the 1/2 power. 81 to the 1/2 power, remember that's the square root of 81, which is 9. So we can simplify that part. And then your exponent property says that you can multiply that 12 and 1/2, and you end up with y to the 6th power. So all I did is simplified what that 1/2 does to the 81y squared. And now I am left with log base 7 of 9y to the 6th power minus log base 7 of 6y squared. So I'm going to go ahead and take care of that subtraction symbol right here, which makes us use division to condense even further. So I have log base 7 of 9y to the 6th power divided by 6y squared. Now, since middle school, you have been working on simplifying your fractions. Well, with logarithms, you're going to do the exact same thing. So I'm just going to go ahead and simplify. I have log base 7. 9 divided by 6 is 3/2. And then y to the 6th power divided by y squared. Remember, your algebra properties on exponents say that you subtract those. So you have 3/2 times y to the 4th power. So this expression would be your final condensed down to just one logarithm. And that's one of the more challenging examples that we have. Here's another one. Go ahead and pause the video. I'd like you to try this one on your own and see how you do. I'll definitely put up all those steps and process to complete this one and explain as I'm going through it as well. So go ahead and pause, copy down this problem, and see how well you can do. So one of the first steps that I did was I took the multiplier that was front and I put it back into as an exponent using that exponent property of logarithms. The next thing that I did was took care of that 4x squared, making that 16x squared, just to kind of simplify my expressions as much as possible before I continue on using any logarithmic properties. So the next one that I'm going to go ahead and do is simplify the multiplication part up top, and then using that minus sign to make a division happen as well. So I went ahead and combined these two with that plus sign, meaning multiplication, and then putting the expression following the minus sign as the denominator of this. Now the next thing that I hope you would notice is that you can simplify this fraction even further. The x to the fifth and the x to the fifth will go ahead and cancel each other out. And then also the 16 divided by 8, that goes ahead and cancels out, leaving us with a 2 up top and a 1 on the bottom, because 16 divided by 8 is 2 and 8 divided by 8 is 1. So just going ahead and simplifying that fraction. So you do have a simplified condensed logarithm saying log base 3 of 2x squared. And that would be your final condensed expression. The next part of this video we'll be talking about solving exponential and logarithm equations. So when you're solving exponential, make sure you simplify so you get the equation on one side to just be the base to the exponent. And then you're going to take the log or natural log of both sides to isolate that exponent to continue to be able to solve for that variable. When you're solving logarithms, you must make sure that you condense to just a single logarithm, using your logarithm properties to isolate that that exponent. And we'll talk about what that means with our examples that you'll see. So here's the first example. 4 to the 3x plus 2 power equals 64. Well, the cool thing about this is that 64 can actually be written as 4 to the third power. So we have both sides having a base of 4. And what we can simply do is just take the exponents and set them equal to each other, just dropping the bases of it. And then going ahead and solving for x. So we're going to subtract 2 and then divide by 3. So we get x in this case to equal 1/3. Here's another example, a little bit more complicated, but this one is in regards to making sure that you simplify everything else. So one of the first steps that I'm going to do is go ahead and subtract 7 from both sides, leaving me with 15e to the 1 minus 3x equaling 3. I'm going to go ahead then and divide by 15 because I need that base and its exponent to be all by itself. And now I have e to the 1 minus 3x equals 1/5. So since you have e, which is the base of your exponent here, all by itself, you need to get rid of that base and being able to get that exponent out of that exponent position. So you have to do the inverse of e, which is in this case actually going to be the natural log. And you're going to have to do it to both sides. When you take the natural log of both sides, what happens to your exponent is it comes out in front. So you're ending up with 1 minus 3x times the natural log of e equaling the natural log of 1/5. Well, the natural log of e, those are going to just go ahead and cancel each other out, leaving you with just 1 minus 3x equaling the natural log of 1/5. So then you can just go ahead and use your basic algebra skills. You can either convert this to a decimal or keep writing it as such. So I would go ahead and minus 1 from both sides. So I have negative 3x equaling the natural log of 1/5 minus 1. And then I'm going to divide by negative 3. So my final answer would say x equals the natural log of 1/5 minus 1 divided by negative 3. Or if you wanted to convert that into a decimal to see if you did this correctly, you would end up with the following value. So here's what you would end up with as a decimal, 0.8698126,375. Obviously, it's irrational and keeps going on. I would personally recommend you use the first 4 and just kind of chop and drop there. Switching over now to solving logarithmic equations. One thing that I see here is I have a log base 4 of 3x minus 2 equals 2. And I need to get rid of that log base 4. So to do that is I need to use exponential properties to get rid of logarithms, because that's how you undo logarithms, or the inverse of logarithms. So I'm going to take 4 to that log base 4 power of 3x minus 2, and what I do to one side I have to do to the other. So what happens is 4 and log base 4 are going to end up canceling each other out. Again, just leaving me with 3x minus 2 equals, on the right side it's going to be 4 squared. And you can go ahead and just simplify that even further to say 16. I'm going to go ahead and add 2 to both sides, leaving me with 3x equaling 18, and going ahead and dividing both sides by 3, leaving me with x equaling 6. Now, with this example, the best thing that I can get you to remember is whatever that base of your logarithm is what you're going to use to get rid of it, turning it into an exponent type situation, which is easier to simplify. Here's another example in which that we will have to use a logarithm property, because remember, you have to condense that logarithm first before you can begin to solve. So I'm going to go ahead, and because it is minus, I'm going to change that to being a quotient. So I have log base 2 of 5 plus 2x divided by 4 minus x, and that's going to be equal to 3. So now that I have it condensed down to one logarithm, I'm going to go ahead and get rid of that logarithm base 2. So because of my base being 2, I'm going to use 2 to get rid of that. Those are then going to cancel each other out on the left-hand side, leaving me with 5 plus 2x divided by 4 minus x equaling 2 to the third power. Or you could say 2 to the third power equals 8. So you can just go ahead and simplify that as fit. And that's what I'm going to do right now too, is simplify that 2 to the third is 8. Now I'm going to continue solving. So I'm going to go ahead and multiply both sides by 4 minus x to undo that division. That's going to cancel out my denominator. So I have 5 plus 2x equaling 8 times 4 minus x. You're going to want to go ahead and do the distributive property to eliminate those parentheses. So you have 5 plus 2x equaling 32 minus 8x. And then continuing to solve for x from there. So you can see my basic solving of a linear equation there once I got rid of that logarithm, and I found x to equal 2.7. Here's the last section of this video regarding exponential and logarithmic equations, and this is particularly about applications. When do we use these two pieces of information? The one area that we're going to focus on is word problems involving logarithmic equations. But in order to do so, we're going to actually use the foundation of y equals ab to the x plus c to start us off with these word problems. So here's the first question regarding Derek and his health. So read over this question and then we will begin. So like I mentioned previously, we're going to want to start out with that foundation of y equals ab to the x plus c. That 75 degrees, which is the temperature of the house, is going to be our c value. It's our baseline temperature. That's going to, no matter how cold his body drops, it will always maintain at that 75 degrees. The next part of the equation that we'll have to find is our a and b value. Now our a value is our initial value and b is our multiplier. And in order to do so, what we're going to do is we're going to make a table to organize our value, where y ends up being the time, and x ends up being the time and y is your degree difference from that baseline of 75. So at 0, we're going to, which is our starting temperature, where the mom takes the temperature of 101.9 degrees. We're going to take that 101.9 and subtract 75 from it to get 26.9. And then 15 minutes later, his temperature is down to 101.2 after taking some Tylenol. So we're going to take that subtraction again, 101.2 minus the 75, and that's going to give us 26.2. Now, using this information, we're just going to go to a basic y equals ab to the x power. And we know a already based off of our table because we know our starting value, and that's what a represents, is our starting amount. So I can set this up already with 26.9 times b to the x power. And I'm actually going to set that equal to 26.2 and put x as 15, so that way I can solve for that b value. Divide by 26.9. The next thing that we're going to do is take the 15th root of both sides to get our b value by itself. And to do that on your calculator, remember you're going to type in 15 and then hit the math button and scroll down to, I believe it's number 5, where you have x and then the radical symbol. And then go ahead and type in that decimal value that we have on the left side. What that tells me is my b value is 99.8. Sorry, I wrote my decimal in the wrong spot. 0.99824. So I have my equation of y equals my a value, which we can get from the table, which is 26.9, times my b value, which we just solved for, which is 0.99824, to the x power plus the 75. So the next thing that we're looking to be able to do with our equation is figure out how long will it take for his temperature to drop to 99 degrees Fahrenheit. So we're going to set his equation equal to 99 and solve for x, which then means that we're going to first subtract 75 from both sides. And then we're going to divide by the 26.9. Just to get that b value isolated by itself. So after subtracting the 75 and dividing by the 26.9, I'm at this point right here where I have 0.89219 equal to my b value to the x power. So how do I get that exponent by itself? And that's where you end up having to take the log of both sides. I'm just going to go ahead and use the common log. And by taking the log of both sides, that allows me to bring my exponent out in front of that logarithm. So I end up with the log of 0.89219 equaling x times the log of 0.99824. Now remember that these logs are just values. So I'm going to go ahead and divide by the log of 0.99824 on both sides to get my x value by itself. So after dividing, I get x to equal 64.75. So we can just approximately say 65 minutes from when he first took his temperature, he will have temperature of 99 degrees Fahrenheit. So here's another example, kind of following that same format of the previous one. You might recognize this one from in class. So as you read through this, remember to start off with y equals ab to the x plus c. But I am going to ask that you try this one on your own. I will do all of the work just like I did in the past, explaining where I get some of the values from. So the first thing that I recognized after completing this problem or reading this problem is that the 54 is the C value because any body temperature will plateau at that given temperature. So then I took the other two temperatures, the 91.3 degrees that they first measured her at, and then also the 10 minutes later temperature of 89.6, and I subtracted the 54 from both of those, and you can see those values within my table. Remember that this 37.3, because it's our initial value, that's going to be our A, and we're going to use that then to be able to solve for B. So I used the equation y equals ab to the x. I plugged in my a value, and then I used my next point, plugged in the 10 for the x value and 35.6 for the y value. And now I'm going to go ahead and solve for b, first dividing by 37.3, and then I will be taking the 10th root to get the b value by itself. So remember, to get the 10th root on your calculator, you're going to want to first type in 10, then hit the math button on the left-hand side, and then I believe it's number 5 where it has the x and then the radical symbol. Then go ahead and type in that decimal, 0.9544, and I found my b value to be 0.99534. So the next thing I'm going to do is go ahead and rewrite my final equation, plugging in my a value and my b value. So we want to know how long ago Grandma died or got ran over by a reindeer. So we're going to go ahead and plug in 98.6 because that's her normal temperature that she runs. And we're going to set that equal to our equation. And we're going to solve for that time, that x value. So I'm going to go ahead and subtract the 54 first and then divide by the 37.3. So like I said, I subtracted the 54 and divided by the 37.3 in that order, and I got 1.1957. Now I have to get that x value, that x variable, by itself. So this is where you would take the logarithm of both sides, and this allows us then to take that exponent and bring it out in front of us, that expression. So here's what it would say. So after taking the log of both sides and bringing that x variable out in front, I'm going to go ahead and then divide by the log of 0.99534 from both sides, giving me my x value. So I get my x value to be negative 38.265. So what that tells me is that Grandma got ran over by a reindeer approximately about 39 minutes ago. I hope this video finds you some helpful examples, some notes to review in preparation for any tests and final coming up. If you have any further questions, go ahead and write them down, and we will talk about them during class. Thanks.